Hello, I'm George Adaimi, and I'll be presenting our work titled Composite Relationship Fields with Transformers for Scene Graph Generation. Scene graph generation includes two tasks. The first task includes detecting the objects in the scene and classifying them. The second task goes one step further and detects the relationship between the pair of objects.
As a result, the scene is represented by a directed graph where the nodes are the objects and the edges are the relationships. Each relationship is represented by the subject, the relationship, and the object of that relationship.
Scene graph generation methods are divided into two groups, top-down methods and bottom-up methods. For top-down methods, images are first passed through an object detector to extract the different objects in the scene. Features for every object are then extracted, and an initial fully connected scene graph is built. The initial scene graph along with the features are then passed through a message passing or refinement mechanism to obtain the final scene graph prediction. The fact that the refinement module operates on every pair of objects makes this type of method inefficient. Bottom-up methods, on the other hand, pass the image through a backbone to obtain the features, then extract different object and relationship representations, which are in turn decoded to simultaneously output the object detections and scene graph prediction. One important aspect of bottom-up methods is how relationships and objects are represented to improve prediction and decoding. In this paper, we focus on relationship representations and introduce composite relationship fields. We encode the relationships in a scene using our composite relationship fields. For instance, we want to represent the relationship riding between the man and the bike. Composite relationship fields turn relationship detection into a dense regression and classification task, where each point in the image has to identify the surrounding objects and the relationships between them. Given an image, for each possible predicate, we output at every point a confidence score and two vectors pointing to the subject and the object respectively, as well as the scale of the related objects. As you can see, only points between the two related objects are responsible for predicting that relationship. Finally, this is how we encode a more complicated scene graph. We are able to obtain good performance using only our fields. However, a missing aspect in previous bottom-up methods is the refinement mechanism, commonly used by top-down methods. But what is the importance of refinement for scene graph generation? Top-down methods rely on refinement since the subject and object of a relationship are highly correlated. For example, we want to predict the relationship between a person and a horse. Given the labels of the objects in this case, it is clear that wearing and carrying are not viable relationships, while riding and on are. Since in bottom-up methods we do not have prior knowledge of objects before predicting the relationships, we introduce a refinement head that leverages transformers for global scene reasoning. Our refinement head consists of a transformer encoder added right after the backbone, which is used to improve the extracted feature map before predicting the composite relationship fields. The transformer encoder allows every location in the scene to attend to other locations. For instance, this location that is responsible to extract the relationship between the frisbee and the person can attend to the objects to better predict that the relationship is throwing. To show that our transformer does attend to related objects, we visualize the attention maps. By passing this image to our model and looking at the attention map for this specific location, for instance, we can observe that the model is attending to certain objects that can be related at this location. Visualizations from other locations lead to the same conclusion. We benchmark our method on the Visual Genome dataset and show that our model obtains state-of-the-art performance for bottom-up methods on the different tasks while running in real time. In that paper, we also compared to other top-down methods. Here we show an example of our predictions of the composite relationship fields. We can see that we are able to extract more relationships than the ones annotated in the ground truth, such as parked on and wearing, indicating that our method is able to reason on the visual scene to extract more relationships. Thank you for your interest in our work. For additional results and details, please find our paper and code online.